Alright, so this is my overview of Quiz 6. So let's go ahead and get started with it. So yes. Alright, so first question was, I asked students if you want to watch from a choice of 5 movies for the rest of your life. Which 5 would they be? Let's find out what the most popular movie choice is. The file's movie.txt contains a list of those results. Each line contains the name of a movie of a student submitted. So before I get started, I'm going to go ahead and comment out all this stuff and see if I can't make sure that I understand this file correctly. The nice thing here is that I was able to figure out how to load these things in, so I could just simply go open movies.txt as though this was a file in your own directory, so you didn't even have to download a file. Just like other questions that are here on this website. It's part of the reason why I really like it. So, data. And this is just simply to test. Actually, I have no idea how big this is. It's just students in my class, but if it's really big, I could really open myself up into pain. So I'm gonna go lines is equal to read. Sorry, gonna go data dot read lines, and then then I'm only gonna print out the first couple lines. Print lines 0 through 10. And now we see that we've got, okay, so Avengers Infinity War, Wolf of Wall Street, Toy Story, Dune, Transformers, Godfather 2, Whiplash. So, and a lot of them end with either a space or a new line, so we'll want to strip that out, as mentioned over here, but that's fine. I went through and sanitized this as much as possible to make sure that Spider-Man was properly hyphenated and stuff. So, that everything works well. Let me just make sure that the recording looks... Yeah, that looks fine to me. Okay. Ooh, I can make myself a little bit bigger of that since we're here. Okay. So now what do we have? So now that we know what this looks like, so we have these movies. First, complete the function below so that returns a dictionary that containing the counts of the movies, e.g. how often a movie was listed. Not all students capitalize their movies, so be sure to convert all movie names to lowercase and strip out any trailing and leading white spaces. Okay. So then second, use the second function to figure out the most popular movie, which in this case was Harry Potter. So I basically my first method in grading this was to see if people got Harry Potter as their output. Okay. So let's go ahead and see. So we've got counts over here. That's what we're going to return. We've got movie counts. It doesn't need to take anything in because I've already provided the functions. But some of you altered that. That's fine. So let's go ahead and just work on it like this. Open movies.txt just like we did earlier. We're going to do it in the read format just like we did earlier. And what am I going to do? I'm going to say this is our data. And that instead of doing read lines, you could do it that way. I'm just going to do 4 line in data. Okay. And I'm going to go ahead and do line. Line is equal to line dot strip. And print line. And hopefully this will let me see. Yeah. So that helps me see that we don't have any extra. Oh, and it's at the lowercase these things too. So I can actually just tag. I can do line equals line dot lower as well, but I can also just do lower over here, which is super useful. Let me pause for a second. My kid is watching cartoons upstairs, so you're going to hear a lot of laughing. Okay, so now we run this again. And I'll definitely want to remove this at the end, this print statement. Make sure that it doesn't... At least for me, I know what happens to my grading flow if I have issues like that. Okay, Sorry if I have a lot of print statements. It kind of just stretches things out. A lot of distance, but it makes this window get really big. Okay. So we've got that. So we've got our lines. Now we need to just count them up. So that's the so the line is the movie name, so I might as well just call it that. Right? Or we can call it the movie, actually, because each line is a movie. So, and again, always thinking about what your variables are and changing the variable names accordingly really helps with understanding this. So if movie in counts. Actually, let's change that. If movie not in counts. If we've not seen this movie before, counts of the movie is equal to 1. Remember, dictionaries are just like lists, except you get to make up what the index is. So here I'm saying the index is the movie name. It's a key value pairing more formally. I mean, where the key is the name of the movie in this case, and the value is how many times we've seen it. We see this a lot. It's a kind of format for counting, counting stuff. It's a very common usage of dictionaries where the key is the thing you're trying to count, and the values are how often we saw each of those keys. Else, if movie not in count, so if we've seen this movie before, counts of the movie is equal to counts of the movie plus 1. One common mistake I saw that for people who did, and I'm going to say this while I'm writing out my test, that did almost everything correct. One common mistake I saw was that they went on autopilot or just tried to use what they've seen in class. And so they tried to do a word count and just simply did every single word. And so they then did split. They then split this up, or they split it up earlier, meaning that things like the Lord of the Rings became the and Lord and of and the and rings, and they counted up each of those words individually. So, let's see. So, run. And so we've now got so now we have an accurate count of all these, and some of you had good choices in movies. Finding Dory's pretty good. Yeah. So, however, yeah, only one of you, however, had the correct answer. The Emperor's New Groove is, of course, the movie that if you had to choose one of them, you could rewatch forever and ever. That is the hill I will die on. All right, so most popular movies. So now we got to take this counts, and we're going to feed it into most popular movie to figure out what the best movie is. So what we do is we say for movie in counts. Is this the correct way to do it? I'm not sure. Why don't I test? I have an IDE. I have an IDE with me, right? Let's go ahead and again test. So, and yeah, that's how to do it. Yeah. Right? So remember, doing the for loop gives you the key, just like that. Okay? So, since I know the key was the movie, that's why it said movie there. And I just tested to make sure that I was, to make sure that my imperfect human memory wasn't playing tricks on me there. All right. So, for moving counts, basically we're gonna need to have most times seen. We could keep track of that, but honestly we don't need to. Okay, so what we want to do is times seen is equal to counts of the movie. And what we're going to do is we're going to say, hey, if times seen is greater than counts of the best movie, time seen is greater than that counts of the best movie, then our new best movie is equal to the movie. All right, so we go through each of the movies. We say, hey, how many times have I seen this? Is the number of times I've seen this movie, is that greater than the number of times I've seen the one that is currently the best? This will not, however, initially work because now this is the way I would normally do it, but this should error, right? Key error, line 16, because this started off uninitialized. So we have two choices. We can either put in a movie name here that we know occurred in there, or we need to make sure, or we put in another if statement, which is that basically all we're going to do is say, hey, if best movie equals blank. This is not the cleanest way to do it, but it works. If best movie is equal to blank, then what we're going to do is we're just going to say, well, this is the first movie we've ever seen, so by definition, it is the best movie. Okay. Now, the more I look at movie, by the way, the weirder the spelling is. Movie. It's very weird. Anyway, so that's one way to fix it. And so we see Harry Potter there. And all I have to do at that point, and more grammatically correct, it would be an else here, and then tabbing that over. Again, another way to do that would have been to just put in a movie that we already knew existed over there. Another way to do that would have been to convert the keys into a list and get the first item out of that. There are a number of ways around that. That was a bit of a headache. But if you had a key error, it was because of this completely unintentional trap I had set up. So that didn't take too long to figure out. So let's move on to the next one. Now this one was a bit trickier. Now the odds were, with what I gave you, were about 41% chance of winning, I believe, for the player to win. I did forget something, and that was that you needed an ace here. I forgot about aces. I'm going to call them one so we don't get too confused, but I forgot about aces. Oh well. That gives you 41. Without the ace, this should bring up the player's odds to about 45%. Some of you noticed that. Good eye on there. It doesn't really, but the odds are still the same. So we're going to take a look at a deck of playing cards. Always useful to have dice and playing cards when you're dealing with statistics, if you're taking a statistics class or anything that's mentioning that they're doing statistics. We're going to take a deck of cards, and we're going to shuffle it, and we're going to split it into 3 random piles, which for me just means pulling it apart like that. So I bet you that a royal card will be at the top of one of each of these piles. Well, at least on one of these piles. If one of those top cards or any pile is a royal, then I win. So if there's no royal, you win. And I helpfully explained that since there's 12 royal cards, right? Aces aren't royal. You've got your queens, got your kings, and they're just flying out of they want to escape. Maybe the French Revolution's come after them. I don't know. Then you got your jacks, right? So there's 12 of these cards, right? And so there's 52 card deck. So 12 winning cards versus 40 losing cards. So the odds must obviously be in your favor. Obviously, though, I presented this in a way that is extremely not. This is in a way that is extremely not fair. It's very much similar to the way. This is a. There are qualitative ways to lie about statistics by asking people. Like one of the more common ones is with any kind of political system. Do you support policy X, which has a name? Okay, like do you support the X Act, right? Versus asking somebody if they support a specific policy. You'll get two different answers, right? So just like this, I've kind of presented this. All right, so but a hint as to what the real odds are. And if you're interested, check out How to Cheat at Everything. You can probably find it at a library somewhere. But the idea here is that the splitting into 3 decks of cards, even though we're splitting it into 3 decks, even though that is something we are totally going to do, it's completely irrelevant, right? Statistically, it's irrelevant. Splitting this into 3 decks of cards and then flipping over the top of each, that's just a way of, that's showmanship, okay? That's just showmanship. It's statistically the same as just taking any 3 cards from the deck. Any 3 of them, right? So, the real odds we need to calculate are if I draw 3 cards from the deck, and if I'm going to draw 3 cards randomly, I could just simply draw the top 3 over here. The question is, how often am I not going to draw a face card? Oop, Joker. We don't need that. And so you can calculate the math on that. But honestly, like I said, a lot of you aren't here to do math. Math is hard, or it's at least intimidating. That's another thing. I say math is hard, but that's like our instinctive thoughts about math. Math is not hard. It's intimidating. So anytime you think math is hard, throw out that thought. Math is not hard. Math is intimidating. I mean, it's got like weird Greek letters. You look at the squiggle and you don't I don't know what that looks like. 2 squiggle is equal to 5 other squiggle? That suddenly becomes really hard because they don't teach you Greek for some reason. But we still use the symbols. Less hard in computer science because we can just simply call it stuff, but we can call the variables what we mean. Okay. So, regardless, like I said, the only difference between having the aces and not having the aces is a difference of about 4% here. So don't worry about it too much. That was a mistake on my part, but it doesn't really affect the answer. So first things first, we need to shuffle the deck. So if we're going to shuffle, we need randomness. This all relies on basically using random in a very nice manner. So first off, random.shuffle. Now this does an in-place shuffle. This is important because some of you did, because this is the correct answer, and some of you accidentally did this, which really messes you up because this function doesn't return anything. So when it doesn't return something, the random.shuffle doesn't return anything. So if we do this, it will give us a none because the deck gets replaced by none. So if we do this, which is the incorrect version, it's not great. See, none. But if we remove this, right, because it's an in-place shuffle, we see. Now, if I wanted to be, let me just make sure this works. So notice what I just did there. 1, 2, 3, 4, 5. Right, and now go back to 1, 2, 3. So when you start up your random function, if you want to be consistent in the statistically random stuff it generates, remember these are pseudo-random, you can totally just do that. is. And that basically says, hey, I want you to use this starting point. If you don't put in anything, it's just going to use the current system time as kind of the loading point for it. So if you want to be able to reproduce your experiments, you use random.seed. That's what random.seed is for. Okay, but we don't need that here. I just saw some students using that. So I figure I might as well tell you what that does. Okay, so we've created the shuffle deck just by doing random.shuffle. That's 3 points right there. Taking the shuffle deck and splitting it up into 3 piles. Okay, so like I said, this is sophistry. Doesn't really matter. So the piles can be any size, but each must have at least 1 card. Okay, so what we're gonna do here is I'm going to basically create my 3 decks. And we're gonna pass in our deck here. I'm gonna treat each pile as a list. So P1 is equal to an empty list. P2 is equal to an empty list. P3 is equal to an empty list, right? And so we're going to split this up. Some of you just split up into even size, but technically if we're just splitting them, they can be any size, so long as they're at least one, got 1 card in them. So that's what I'm going to do here. What I'm going to do here is I'm going to do something a bit. Normally we choose. It's gonna be a bit big brain here. But what I'm gonna first do is that to make sure that we have a card in each of them, I'm gonna take the first card in each and put it in here. Again, cards, the actual position doesn't matter. So P1 is equal to. So let's do P1 dot append deck 0. All right, and then we're gonna copy and paste, and we are going to do 2, 3, 1, 2. Okay, and then for card in deck. But we've already done the first 3 cards, so we don't want any repeats. That would mess things up considerably. So what we're going to do is say, for every card in the deck, what are we going to do? I'm going to just simply, instead of use the first 3, I'm going to go, well, we've done 0, we've done 1, we've done 2. So I'm going to start from 3 and go to the end. I'm going to do a slice over there. Again, there's lots of ways to do this one. This is the way that makes sense to me. So for every card... And this is where I get a bit silly about here. Piles are equal to, and I'm going to make a list. P1, P2, P3. This is the big brain move here. We could do it just by simply. Okay. Before I explain that, let me go ahead and just simply. We want to randomly distribute these cards in the pile. One way to do that is pile num is equal to random.rand int 0 to 2. Now, if I recall correctly, let's go ahead and just double check, right? Random.rand int. Right. Right, if we do rand int, that is inclusive, I believe. Except that's numpy, which is... And I just want to be very... Because I don't have my IDE over here... Docs. There we go. Yep, it's inclusive. It's like the only thing we do that's inclusive. So, if pile num... equals 0, then P1 dot append card. And let's call 0 to actually it's 1, 2, 3. So why don't we do 1 through 3? That way we don't have to keep translating by -1, right? Okay, 2, 2, 3, 3, and then we can return if we need to return multiple things. By the way, this is the way you do it. You do return P1, P2, P3, which gives us a tuple. It gives us, we can only ever return 1, 3, but what this does, it gives us a tuple, which is a lot like a list. If you remember your textbook, it's a lot like a list, but in one kind of grouping. It's one of those cool things Python will do. Otherwise, you can always just return them in a list like this. It doesn't really matter how to do it, but the point being is that how did I split them up? I said for every card, starting with the index 3, because we already did 0, 1, and 2, we chose a pile at random. So what was my big brain move? My big brain move was, instead of doing that, I put them in a list together. I combined them together, and then I'm going to use random.choice for the piles. And then then all 6 of those lines condense into one. Target pile dot append card. Now I'm pretty sure I've done this right. So what we're gonna do to make sure that I've done this right, of course, is test what you do. Return piles. Okay. Create 3 piles. Calling create shuffle deck. And bad input on line 22. Aha, I accidentally copied that. Okay, it worked. It just, remember, I keep forgetting that it doesn't do anything if I don't put a print statement. And there we see that we have 3 randomly sized piles. And you see that the first pile becomes, alternately bigger and smaller, which is pretty cool. Okay, so we've got our 3 piles. Selecting the top 3 cards. Oh my. So we can actually just simply do a game now. Let's go ahead and actually just simply put this in. Yeah, def game is equal to yeah, let's just get these guys. Piles is equal to create these 3 piles, which is a list in this case. All right, and I can just simply get my these 3 variables back out pretty easily if I want to, by just simply saying, and the like. But I have no need to do that. But I've got them in a variable grouping together. That's all I need. Okay, so top cards is equal to its new. We're gonna make a new list with that. So for pile in pile. So for each individual pile, what am I gonna do? I'm gonna say top cards dot append. We want the top card, right? Which would be pile 0. Okay. And we're not ready to return anything yet, but I'll go ahead and print top cards. Making sure that I'm still recording and I haven't been wasting 25 minutes being paused. Okay. So now we can also just call game fairly easily, and boom, 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 boom. Great. So we have the top cards. That is 15 points. That is half credit now. Now let's determine who won. See how this rubric kind of led me to what I needed to do? It even with the toughest part, if I couldn't figure out the toughest part, there were ways I could have gotten around it. I could have said, all right, assume these things, if I thought that was too hard, I could have come up with an alternate answer, which is perfectly fine. There are things that we can do about that. Such as, I'm just going to take the top 3 cards of the whole deck, which is statistically the same. And that would have at least gotten you a huge amount of partial credit on that small portion of it. And then you could have moved on and gotten full credits on these other parts. So determining who won. So who won? So if I draw so what is this? I win. So I'm going to win if any of the 3 piles is a royal. So if K in top cards, and you got to be explicit. There was no way to do I saw one student who did something not exactly this but similar logic, or J or Q, right? Those are all, you can't do that. You have to be explicit, because otherwise those will be truthy and evaluate to true. So if K is in the top cards, or Jack or Queen, we'll return, I'll return true for Rosen winning, because I'm Rosen. Else, return false, which I can always just simplify by doing this. Print game. And it alternates between true or false. One thing that I saw with the common problem is that when students played this game, they created the deck, they shuffled it, they created the piles, and then when they repeated it 1,000 times, they used the same deck each time. And the same piles. They didn't reset it, and so they always won all the time, or they lost all the time. Okay, and 100,000 was a bit much for this one, but that's okay. We'll get around to that. So, okay. So simulating this game 100,000 times. Once you have a game function that returns what you want, this is the easiest 5 points you can ever get. That part is done. Okay, now we need to calculate the real odds, which is so let's go ahead and say Rosen wins is equal to 0. Let's go ahead and back off and make this trials. We'll start out with 1,000 just to be safe. And then we'll build up to it, because we don't necessarily want it to freeze. So, if that's true, Rosen wins plus equals 0. No need to keep track of who else wins, because that can be figured out via subtraction. You don't need to, but you can. Now to figure out the real odds, print Rosen Rosen wins divided by trials, and then 1 minus Rosen wins divided by trials. Figure out the number of times Professor Rosen loses, which is the number of times the player actually wins. Oops. Trials is not defined on line 33 because I am bad at spelling. 0, 1. Up. Plus equals 0. Plus equal 1. Silly me. And we get something. And again, without the ace, which is our 1, we'd get something closer to this. It's closer to 41%. We still... So, let's go up to 10,000 and put the ace back in. You can call it a 1 or an ace, but I like that the letters were helped with making that. We see that, and so this should not be too much. It might take it a bit of time, but let's see. There we go. Pretty clean division there. Okay, so those were the real odds. My main thing for my main advice for these kinds of problems for the exam, for the Monte Carlos, don't overthink them. Use that rubric as a guide if you don't know where to start. If I'm saying, hey, shuffle something, then focus on shuffling it. If I'm saying, hey, I want you to create one of those fate dice that we saw, that I showed you before. You know, create a function that does that. The only hint I'll give you about the final exam with this question is that it's a cooperative game with multiple players. But because it's a cooperative game and every player does exactly the same action, the number of players doesn't actually matter. It doesn't matter if there's 1 or 100. That has no impact on the game. The players are literally taking turns to do the same thing, working as a team. Okay, so questions like the other one. Right, I've mentioned that what that one does. So I've mentioned with this, what we're doing with this one, okay, is that I will give you a file. I will give you a file, an example input, example output file. And if your code can get to matching my file, that's that. Regular expressions will greatly help you on this one because you'll be looking for a pattern. I don't plan on making the regular expression too arduous, but because you're able to use regular expressions, you can use the re.sub. You're going to be doing something very similar to this, but it's more similar to the Social Security problem. Right? Reading that problem, reading the file, and then writing out a new one. Remember, to write a file, what you just simply do is that you create your file by doing open the file name, which is going to be different, something like output.txt or whatever, and a W over here, and then that becomes your variable there. And then to write data, you do like output.write or data.write or whatever you call your file. The only thing when writing is that's different than printing is that, right? So if I had a file called like output is equal to open exam out.txt and W, that's how I'd create a file for writing. The next thing you'd want to do to write is output.write, and then whatever string you need to write out, be it from a variable or whatnot. Okay? But at that point, what do you do? Well, the only thing you have to be aware of is that if you want extra new lines, and this shouldn't come up during the exam because you're you're replacing one line with another. You're just swapping out stuff in the line, so there's no need to add extra new lines. But if you wanted to add but print puts in extra new lines for you, write does not. So just be aware of that. So if you get extra new lines, that's because you don't need. That's because you added in a /n over here. On the exam, you shouldn't have to worry about that though, because you're just simply taking one line, modifying it, and writing it back out. All right. If there are any issues with grading for this one, please let me know. I should have graded them all.